In this video, we will see another number theory algorithm, the naive primality test. With this test, we can decide whether a number is a prime or not. During this algorithm, we iterate through numbers which are smaller than the investigated number, and if any of them divides the number, then it isn't a prime. If the investigated number is very big, then we need to do much more iterations and it requires too many operations. How much big numbers do we need? One of the most well-known procedures in modern encryption is RSA, which works with primes that have more than 100 digits. Imagine how complicated it is to check the primality of this number with the naive primality test. Because of this, we can do some preparing on the algorithm. Do we need to iterate through all of the numbers which are smaller than the investigated one? Can we not find a smaller boundary? Let's see the number 25. If we start dividing it with the numbers which are smaller than 25, then we will divide it with some numbers which power also less than 25. For example, if we divide it with 2, then we will divide it with 4, 8 and 16. If we divide it with 3, then we will divide it with 9. In case of 4, we will do the same with 16. What follows from this? It is enough to do the iterations up to the square root of the investigated number. Let's see how it works with an example. Number is 16. So we know that it is enough to check the numbers until 4. The first number, 2, is divides 16, therefore 16 is not a prime. Let's see another example, 17. The square root of 17 is 4.12, so it is enough to check the number until 4. 2 doesn't divide 17, 3 doesn't divide 17, and 4 doesn't divide it either. Therefore 17 is a prime. Let's see the source code. We will check whether any of the numbers which are smaller than the square root of the number can divide the investigated number. Start a loop from 2 until the square root. If any of the numbers divide the original one, then we return with false. Otherwise, after the loop, we return with true. The time complexity is ordo square root n. With very big numbers, there are also too many operations. Another repair is that it is enough to check the primes which are smaller than the square root of the number.